When we left off last time, we were looking at shaders. When a GPU, quick review, when the GPU tries to draw a triangle, it looks at every pixel that it's gonna draw, and it runs it through a fragment shader to figure out what color it should draw to the screen. And we looked at how to draw a very simple texture. But now, today, we're gonna start looking at lighting systems and how to light an object. And you'll have to forgive my voice because I just had a cold, so it sounds a little bit different, I understand. So today we're going to look at Lambertian surfaces. Let's say we have an incoming light source. It's coming in like so. And these light sources are parallel and very strong, like the sun. In video games, this is called a directional light source. Okay? Some guy named Lambert figured out that the apparent intensity of light striking a surface changes with the slope of that surface. So if your surface is at a steep angle, then the light striking it will be kind of dim. But if the surface is facing the light rays are hitting the surface dead on, then the apparent brightness of the light on that surface will be a little bit brighter. So in formal terms, this is called Lambert's cosine law. And it is that the intensity of light on a surface is equal to the cosine of theta. And let's take a look at what theta is. On this surface right here, let's find the normal of that surface. Here it is. Normal is 90 degrees to the surface. And then also the direction that the light is coming from. And the direction the light is coming from is easy. You just reverse wherever. So this is our incoming light. It goes right to left. So the direction the light is coming from is it just goes straight to the right. And the theta that we want is this angle right here, the angle between these two vectors. Cosine of this theta will be the apparent intensity of light on the surface. Here's another example for this surface right here. It's straight up and down, so this normal heads straight to the right, and the direction to the light is the same vector. It heads straight to the right like this. And so these are both at right angles to the surface, and so they're really the same vector. The theta between these two vectors is 0 degrees. So cosine of 0 in this case is 1. And so you're going to have a much brighter light on this surface than on other surfaces. But for this surface, you see it's slanted, it's tilted away from the light, and so this theta grows large. And here's what cosine looks like up here. Here's 0. Okay. As the angle, this is theta, and this is cosine theta. As theta increases, cosine theta starts to decrease until right here at 90 degrees, now cosine of theta is 0. So when the surface, I mean, if you think about it in terms of, take a piece of paper and put it up to the sun. If it's facing the sun, it's going to be a nice bright sheet of paper. That's when cosine of theta is 1. If it's facing away from the sun, it's not going to get any light, and that cosine of theta is 90 degrees is going to be 0. So, but the problem is that we actually don't know what this theta is. We don't know what theta is. We know what these vectors are. This right here is the L vector. That's the vector that goes to the light. And we can calculate that really easily. We just look at the light vector and we flip it around. Easy. This vector right here is the normal of the surface. And we have that data too. The video card will pass us that normal, very, very simple, very easy. But we would have to calculate the theta between these two vectors. Well, we're not going to do that. We're actually going to use a trick. You remember that the dot product, switching to another color real quick, A dot B is defined as the length of A times the length of B times cosine theta. And this would be a good time to review the dot product videos if you've not already. But in this case, the normal vector is unit length. I drew a little hat over it. So this will be 1. This will cancel out. And the direction vector to the light, we're going to normalize it. It will be also unit length. And so that will be 1. And so you get A dot B equals cosine theta. That's all you're left with. Or in other words, the vector L dot with the vector N is just, and really these should both have a hat, they're both going to be unit length, is cosine theta. So L dot N is cosine theta, and Lambert's cosine law is cosine theta. That means we can call Lambert's cosine law is just L dot N. That's how we're going to calculate. Because cosine is a transcendental function. We don't even want to calculate cosine. That's an expensive function to calculate. We want to avoid it if we can. And we can. It's really easy to avoid it. We just use the dot product instead, which is just a few multiplications and additions. And then bam, we're done. So now there's one remaining problem, and that is that this normal vector n is actually in the local space of the object when we get it from the video card. Whereas this L right here is in the global space. So we have to either transform L to be in local space of the object or N to be in global space of the object. And as it turns out, it's much easier to transform N to be in the global space than it is for L, because if we wanted to transform L into the local space, then we would have to invert a matrix. So we have G, which is the, let me go to a different color, which is the global space matrix transform that takes things from local to global space. So we're going to multiply that times the input normal vector that we get from the video card. And that is going to give us a global space transform. And then a global space transformed normal vector n. And we dot that with L. And that is our Lambertian surface lighting value. And note that this is only applicable for a directional light source. So a point light source like a lamp, you have to do some other things for it to be valid. But for something like sunlight, this works perfectly. So let's go, there are a few gotchas that we got to cover. Let's go see what they are. So here's our first look at the shader language, GLSL. And you can see syntax-wise, it's pretty similar to C++ that we've been doing so far. There's also HLSL and CG and a bunch of other ways that you can write shader programs. But we're just going to work with GLSL, and we're going to learn the math because we like math, and the math is the fun part. So let's go over these caveats that we need to think about. First is that the global vector that transforms us from local to global space is a 4x4 vector. You can see the type is mat4, and we need a 3x3 vector. So we use this cast right here to grab the upper 3x3 part of the matrix. This is the rotation components only. If you remember from our matrix videos, the upper 3x3 holds rotation and scaling, but there's no scaling in this matrix, so it should be just the rotation. And we make a new global 3x3 object matrix. And then we multiply it by the fragment normal. The fragment normal is in local space, and we multiply it through our global matrix to get it into global space. And then we have to normalize that because the reason is that the video card does some wonky stuff when it's doing the linear interpolation that can sometimes cause the normals to be, the normal vectors to be denormalized. And I may cover that in a future video, but for now we're just going to normalize it just in case. So we get a new global space normal vector. So now let's do our dot product. We're going to take the dot product of the sunlight vector, And I put a negative here because we have to reverse that direction. And the global normal vector. There we go. Now let's come down here and see what the rest of the shader does real quick. Here I actually remap it, I fudge it. You see this a lot in video games actually. The default lighting values are actually a bit harsh, and so I do a remapping so that they're a little bit less. I pull down the brights, they go from full to 90%, and I pull up the darks. Any completely dark value gets about a 40%. So this makes it seem a little bit less contrast, and so that there's a little bit more ambient light in the scene. And then we move on. I multiply the current light level with the surface color, whatever surface color that the object is, and that gets me a diffuse value. I then multiply that by the texture, and that factors in whatever texture. This is the previous video that we talked about, and then I set that as the output color, and we're done. This last one is if a fragment is so transparent that it can hardly be seen, then we discard that pixel and don't draw anything. But that's optional. Here's where the real work is right here. We set the output color to the diffuse color that we calculated. If that's a little too much for you, don't worry about it. We're going to be doing a lot of this in future videos. You're going to get lots of practice. And again, all of this code is available on GitHub. You can build it and compile it, mess around with it, do anything you like with it. You just look in the description. The link is in the description. So that'll show you all that stuff. So here we are in the game, and we can see you cannot see the sunlight, but I've programmed it so that the sunlight is constantly rotating overhead so that you can see the effect of all this stuff. You can see that the darks aren't completely dark because we did that remapping. And so that's it. We're going to continue in the next few videos. I'm not exactly sure what we're going to be doing, but it is going to be shaders and lighting profiles and that sort of thing. So see you then.